Combinatorics, Lecture 8, Möbius function. Let us start with the notion of a binary relation. So let X be a set. Definition: a binary relation on X is a subset of the Cartesian square of X. So, which means that a binary relation consists of pairs of elements of X. Notation: if we have a subset rho of X times X, then the fact that the pair A, B belongs to rho is usually written as A rho B. Example 1. For any set X, we have the so-called equality relation on X, which is usually denoted by this symbol. It consists of all pairs A, where A is an element in X. And this is usually written as that A is equal to A. Example 2. If we take as X the set of all real numbers, then we have the usual order less than or equal to on real numbers. It consists of all pairs A, B of real numbers, such that A is less than or equal to B. Example 3. On the set of all integers, we have the order which can be described as A divides B. So two elements are related if and only if the first element divides the second element. So this is the divides relation. Example 4. On the set of all people, we have the binary relation A is a parent of B. Now let us discuss the notion of a partial order. Let X be a set. Definition: a binary relation rho on X is called a partial order, provided that it has the following properties. First of all, rho is reflexive, which means that it contains the equality relation. So A rho A for all A in X. Second property is that rho is transitive. This means that A rho B and B rho C implies A rho C for all A, B, and C in X. And the third property is that rho is antisymmetric. This means that if A rho B and B rho A, this should imply that A is equal to B for all A, B in X. Example 1. If we take as X the set of all real numbers, then the usual order less than or equal to on the set of all real numbers is a partial order. Example 2. If we have a set X and consider the set 2 to the power X of all subsets of X, the so-called Boolean of X, then on this Boolean we have the relation of being a subset. This is a partial order. The usual notation that if less than or equal to denotes some partial order, then the notation less than usually denotes the relation given by that A is less than or equal to B and A is different from B. Notably, the notation for subset is an exception. One usually, if we have a proper subset, this is denoted by this more complicated symbol. Now we can talk about partially ordered sets. Let X be a set, and less than or equal to be a fixed partial order on X. Then the pair consisting of X and this fixed partial order is usually called a partially ordered set, also known as a poset. For example, the set of all real numbers with respect to the natural order is a poset. Example 2. The Boolean of any set with respect to the order which is given by the subset relation, also one can say the order given by inclusions, is a poset. Remark: if X is a poset with respect to some partial order less than or equal to, then any subset Y of X inherits the structure of the poset with respect to the restriction of this partial order to Y. So we consider the relation, let's denote it for the moment by less than or equal to prime on Y, which consists of all pairs A, B in Y, Y, such that A is less than or equal to B in X. And usually this relation less than or equal to prime is denoted by the same symbol, less than or equal to. Next, let us discuss the so-called covering relation for partial orders. Let X be a poset with respect to some partial order less than or equal to. Definition: for two elements A and B in X, we say that A covers B, provided that A is different from B, B is less than or equal to A, and for any element C in X, which is greater than or equal to B and less than or equal to A, it follows that C must be either A or B. There are no proper intermediate elements between A and B. For example, if we take the Boolean of the three-element set consisting of A, B, and C with respect to inclusions, then the subset A, B covers the subset A. Note that the cover is usually not unique. Here, the subset A, C also covers A. It's another cover. Example 2. If we take the set of all real numbers with respect to the natural order on real numbers, then if you take any real number A, there is no element in real numbers which covers A. So covers do not have to exist. Example 3. If we take the set of all integers with respect to the natural order, then for any integer A, the element A plus 1 covers A. Example 4. If we take the set of all positive integers with respect to the divisibility order, then the element 10 covers both 2 and 5, because 10 is equal to 2 times 5, and there are no intermediate numbers between 2 and 10, and there are no intermediate numbers between 5 and 10, which divide each other. It is convenient to draw partially ordered sets using the so-called Hasse diagrams. So a Hasse diagram of a partially ordered set is an unoriented simple graph whose vertices are elements of the poset, and edges represent the relation A covers B, and usually in this case A is drawn above B a little bit. Not necessarily strictly above, but in some sense above. So here's an example. This is the Hasse diagram of the Boolean of the two-element set consisting of A and B with respect to the inclusion order. So the smallest element here is the empty set. The singleton A covers the empty set, and the singleton B covers the empty set, so therefore we draw it like this. And the set A, B covers both A and B. And then this gives us the complete structure of this partially ordered set. Next, we need to talk about the incidence algebra of a poset. Let X be a finite poset with respect to some partial order less than or equal to. Definition: the incidence algebra of this poset, over we need to fix some scalars, so let's choose real numbers, so over real numbers, is a set which we denote by I of X of all functions with two arguments, where each argument is an element in X, and the value of the function is a real number. But we put one condition. We put the condition that the value is non-zero only in the case when the first argument is less than or equal to the second argument. So here we use the structure of a poset. This set, I of X, has a natural structure of a real vector space given by pointwise addition and multiplication with real scalars. As usual, functions into a vector space is a vector space. Moreover, this set has the natural structure of an associative algebra given by the following convolution of functions, we denote it by star. So if we have two functions f and g in I of X, and two elements a and b in X, we define the value of f star g at the pair a, b as the sum over all intermediate elements c, so c should be greater than or equal to a and less than or equal to b, and then we take f of a, c and multiply with g of c, b. And we explain why this is associative. So from the formula directly it's completely unclear why such an operation should be associative. The associativity we explain on the next slide. So let X be a finite poset with respect to some partial order less than or equal to. It is easy to see that since X is finite, there is an element which is minimal, and then we take it out, we take the next minimal element, and so on. So we can write the elements of X in the order, so A1, A2, and so on, AK, such that AI is less than or equal to AJ implies that the index I is less than or equal to J, and here this is the usual order on integers for all I and J. Note that this is not unique, and here we make some choices. In any case, if we fix such an order, we can represent the elements of I of x as upper triangular matrices. So we have a matrix where rows are indexed by A1, A2, and so on, AK, and columns are indexed by A1, A2, and so on, AK, and in the intersection of row I and column J, we write the value of our element in the incidence algebra at the pair AI, AJ. And in this way, directly from the definitions, our convolution of functions corresponds exactly to matrix multiplication. If we look at the formula for convolution, that's exactly the formula for matrix multiplication, and we know from linear algebra that matrix multiplication is associative. And this implies that the incidence algebra is a finite-dimensional associative algebra. This algebra also has the unit element, which we will denote by this bold 1, and this is represented by the identity matrix. So this is a function whose value at any pair A, A is 1, and whose value everywhere else is 0. Let's do one example. So consider the Boolean of the two-element set, elements are A and B, with respect to inclusions. So we order the elements of this Boolean as follows. We start from the empty set, then A, then B, and then the whole set A, B. And then if some subset is included into the other subset, then the other subset is to the right. So this is how we want to write our elements. And then the elements of our incidence algebra are represented by the following 4 times 4 matrices. Note that we have here a 0 entry in the second row and in the third column. So this represents the fact that A is not a subset of B. So A and B, two singletons, they are not ordered with respect to our partial order, so the corresponding value must be 0. And the stars represent the points where we potentially might have non-zero values. So I of x consists of all matrices of this form, where we, instead of any star here, we write some real number. Now we can talk about the so-called zeta function of a poset. So let's assume that x is a finite poset and consider its incidence algebra. This algebra has a specific element which is called the zeta function, and it is defined as follows. The value of zeta at any pair A, B such that A is less than or equal to B is equal to 1. So in our previous example of the Boolean of a two-element set with respect to inclusions, the zeta function is represented by this matrix. So it has value 1 at all places where the non-zero value is allowed. Note that zeta is represented by an upper triangular matrix with 1s on the diagonal. So in particular, this matrix is invertible. And what we are going to do now, we will show that the inverse of this matrix is an element of our incidence algebra. So zeta function is actually an invertible element of the incidence algebra. And the inverse of the zeta function is called the Möbius function. That's exactly the subject of today's lecture. So we define the Möbius function, which is denoted by mu. That's an element of the incidence algebra, which is defined by the following recursive procedure. So the value of mu at the pair A, B equals 0 if A is not less than or equal to B. That's the condition of the incidence algebra. It's equal to 1 if A is equal to B. And if A is strictly smaller than B, then mu of AB is defined recursively as minus the sum over all elements C, which are greater than or equal to A, but strictly less than B, and then we take mu of A, C. So this function is called the Möbius function. So for example, our running example of the Boolean of the two-element set with respect to inclusions, the Möbius function will be represented by the following matrix. So we have 1, minus 1, minus 1, 1 in the first row, then 0, 1, 0, minus 1, 0, 0, 1, minus 1, 0, 0, 0, 1. So we have this 0 here because it's an element of the incidence algebra. And the zeta function was very similar, but everything was 1. And now it's very easy to check that if we take the matrix where we have 1, 1, 1, 1, 0, 1, 0, 1, 0, 0, 1, 1, and 0, 0, 0, 1, and we multiply that matrix with this one, we get the identity. So in this particular case, we immediately see that the Möbius function is the inverse of the zeta function. And this will be our proposition. So proposition, the multiplication of mu with zeta in any order is equal to the identity. Proof. Since both zeta and mu are represented by square matrices, it's enough to prove that their multiplication in one order is the identity. So we prove that mu times zeta is the identity. Let A and B be two elements in X such that A is less than or equal to B. If A is equal to B, then mu times zeta evaluated at A, A equals mu of A, A times zeta of A, A, which is 1 times 1, which is 1. That's great. If A is strictly smaller than B, then mu times zeta evaluated at A, B is equal, according to our rule for the product of two functions for convolution, the sum over all C between A and B, mu of A, C times zeta of C, B. Zeta has value 1, so it's just mu of A, C times 1. But then this 1 we can forget, and we see that the sum is equal to 0 due to our recursive definition of mu AB. We defined mu of A, B as minus the sum over all C, which are strictly smaller than B here. So this gives us 0, and that proves our proposition. In other words, the function mu is indeed the inverse to the function zeta in the incidence algebra. And the matrix of mu then, of course, is the inverse to the matrix of zeta. Here is an example. Consider the poset given by the following Hasse diagram. So we have 1 and 2 at the bottom, then 3 which covers both 1 and 2, and then 4 which covers 3. So here are the matrices for zeta and mu respectively. The matrix for zeta is 1, 0, 1, 1, 0, 1, 1, 1, 0, 0, 1, 1, 0, 0, 0, 1. So we only have 0 here in row 1 and column 2. This is because 1 is not smaller than 2 in this poset. And the matrix for mu is 1, 0, minus 1, 0, 0, 1, minus 1, 0, 0, 0, 1, minus 1, 0, 0, 0, 1. And this is, so mu on the diagonal must be 1, and then for 3 it should be minus the value on the diagonal. So it should be minus 1 here. And for 4, it should be minus the sum of these two values. But 1 plus minus 1 is 0, so it should be 0 here. Similarly, if we start with 2 in the second row, and similarly in rows 3 and 4. So in particular, mu of 1, 1 is 1, mu of 1, 2 is 0, because 1 is not less than or equal to 2. Mu of 1, 3 is minus 1, it's minus this number. And mu of 1, 4 is 0. It's minus 1 plus minus 1. So the Möbius function is fairly easy to compute if you do this recursive procedure. And now, why is Möbius function interesting? It's interesting because of something which is called the Möbius inversion formula. So let x be a finite poset, and f some function from x to r. Define the function g from x to r as follows. The value of g at some element a of x is equal to the sum over all b which are less than or equal to a, f of b. So we get g by adding up all values of f below some fixed point, or equal to that point. Theorem, the Möbius inversion formula, for any a in x, the value of f at a is equal to the sum over all b which are less than or equal to a, g of b times mu of b, a. In other words, if we know the function g, we can recover the function f using Möbius functions. So the use of Möbius function is to inverse this procedure. We started from f and made this summation to obtain g, and using the Möbius function we can go back. Proof. So we represent both f and g as row vectors with entries f of a respectively g of a for a in x. Then g of a is equal to the sum over all b less than or equal to a, f of b, and then we can write zeta of b comma a because that's equal to 1. But this means that the vector of g is obtained from the vector of f by multiplying with the matrix of zeta on the right hand side. Now if you take this equality and multiply with the matrix of mu, and use that the matrix of zeta is the inverse to the matrix of mu, we get that the vector of g times the matrix of mu is equal to the vector of f. And the expression that the vector of g times the matrix of mu is equal to the vector of f, if we write it with respect to the entries of these vectors and matrices, we get that f of a is equal to the sum over all b which are less than or equal to a, g of b times mu b comma a. And this is exactly the Möbius inversion formula. Let's look at some examples. Example 1. For a positive integer n, consider the set n underlined, that's a set of all integers 1, 2, 3 and so on up to n, with respect to the natural order. So this is a poset where the Hasse diagram is just a vertical line. Then the matrices of zeta and mu here are as follows. The matrix of zeta is the upper triangular matrix of size n times n, where above the diagonal everything is equal to 1, because any pair of elements is comparable. And then the matrix of mu, it's a matrix where the main diagonal consists of 1s, the diagonal just above it consists of minus 1s, and the rest is 0. So one can easily check that the product of these two matrices is the identity matrix. So in other words, in this case, mu of a comma b is equal to 1 if a is equal to b. It's equal to minus 1 if a is equal to b minus 1, and it's equal to 0 otherwise. So if our function g is obtained from f by adding up over all smaller numbers, so g of a is equal to sum over all b from 1 to a f of b, then f of a is equal to the sum over all b from 1 to a mu of b comma a g of b, and it's equal to g of a minus g of a minus 1 for any a greater than 1. Example 2. For a finite set x, consider the Boolean of x with respect to inclusions. Claim, for each pair of subsets of x, a and b, such that a is a subset of b, the value of the Möbius function at the pair a comma b equals minus 1 to the power the cardinality of b minus the cardinality of a. To prove this, we need to show that the sum over all intermediate subsets c between a and b of minus 1 raised to the power the cardinality of c minus the cardinality of a is 0. So if we fix some cardinality k between 0 and the difference between cardinalities of b and a, then there are exactly the difference between the cardinalities of b and a, choose k, choices for c between a and b such that the difference between the cardinalities of c and the cardinality of a is k. And so our summation formula, which we want to prove, really becomes the sum over all possible cardinalities k from 0 to the number of elements in b minus the number of elements in a. Then our binomial coefficient, the cardinality of b minus cardinality of a, choose k, and then minus 1 to the power k. But here we can immediately recognize this formula. The left-hand side is 1 minus 1 raised to the power the cardinality of b minus the cardinality of a using the binomial formula. So this equality is indeed true, and this completes the proof of the claim. Here's how we can apply it. So the corollary from this is that for finite sets x1, x2, and so on, xk, the cardinality of the union of x1, x2, and so on, xk equals the sum over all non-empty subsets S of k underlined minus 1 raised to the power the cardinality of S plus 1, and then we take the cardinality of the intersection of all xi's where I runs through S. And this is what we know as the inclusion-exclusion formula. So the inclusion-exclusion formula is a corollary for the Möbius inversion formula for the Boolean. Proof. If we take a non-empty subset S in K underlined, we can define G of S to be the cardinality of the intersection of all xi's where I goes through S. And we define F of S as the cardinality of the same intersection minus the union over all oversets T of S, which are different from S, and then we intersect xj's where j is in T. So we claim that G of S is equal to the sum over all T between S and K underlined F of T. So we will prove this claim later. Now let us assume that this claim is true. If this claim is true, then we can use the Möbius inversion formula and recover F from G. So F of S is equal to the sum over all T between S and K underlined, the Möbius function minus 1 to the cardinality of T minus cardinality of S, G of T. But the original inclusion-exclusion formula is exactly the same when you take S to be the empty set. So for S being the empty set, you should interpret the corresponding expression as the left-hand side of the inclusion-exclusion formula. Let's prove the claim. So we prove that G of S is a sum over all T between S and K underlined F of T. So F of S is the cardinality of the following set. We intersect all xi's for i's in S, and we throw away the union of intersections of all xj's where j runs over arbitrary proper overset of S. But this means that F of S counts exactly the elements which belong to the intersection of all xi's, but not to any intersection of bigger number of xj's. At the same time, the value G of S is just the cardinality of the intersection of all xi's, where I is in S. And then this immediately gives us the formula which we want to prove. So as we see, the inclusion-exclusion principle is a consequence of the Möbius inversion formula applied to the Boolean of a set. So because of this, one can say that Möbius inversion is a very vast generalization of the inclusion-exclusion principle. Example 3. For a positive integer n, let us consider the set 1, 2, 3, and so on n with respect to the divisibility order. Claim: the Möbius function for this set is given by the following formula. So if k and m are two elements in the set n underlined and k divides m, then the value of mu at the pair k, m equals 1 if k is equal to m. It's equal to minus 1 to the power s if m divided by k is a product of s different primes, and it is equal to 0 otherwise. To prove this formula, we need to show that this satisfies the recursion for Möbius function. So we need to show that the sum over all k which divide m of mu k, m is equal to 0 if m is greater than 1. So let p1, p2, and so on ps be the distinct primes that divide m. Then, when we write down explicitly and only look at the terms which are non-zero, we need to prove that the sum over all t, the subset of S underlined, the value of mu applied to m divided by the product of all pi's over I in t, m is equal to 0. And again, using the binomial formula, this reduces to the expression 1 minus 1 to the power s is equal to 0, just like for the Boolean. So now we can discuss the classical Möbius inversion, and that's a Möbius inversion for the order of integers with respect to divisibility. So let f be a function which is defined on positive integers and has real values. Define the function g from positive integers to real numbers as follows. G of n is equal to the sum over all divisors d of n f of d. This should be g. And now we have the corollary, which is a classical Möbius inversion. F of n is equal to the sum over all divisors d of n mu of d comma n g of d. And quite often here one uses a notation mu of n divided by d instead of mu of d comma n. So in this way, Möbius function becomes a function with one argument, and this is due to the fact that the value of our Möbius function at the pair d comma n only really depends on n divided by d, and not on each argument separately. So this is a classical Möbius inversion. Okay, so some additional problems and questions at the end. Problem question 1. Check with all details that for any poset x, any subset of x inherits the structure of a poset with respect to the restriction of the partial order. Problem question 2. Prove that any finite poset has a minimal element, that is an element A, such that b is less than or equal to a implies b is equal to a for any b. Problem question 3. Use problem 2 to show that the elements of a finite poset can be written in the order a1, a2, and so on, an, such that ai is less than or equal to aj implies I is less than or equal to j. Problem question 4. Check with all details that the bold 1 function, the element of the incidence algebra, which is defined via the Kronecker delta, is in fact the unit element of this incidence algebra. And problem question 5. Fill all the details for the computation of the Möbius function for the natural numbers with respect to the divisibility order. Thank you very much, and see you next time.